G'day, Doug Williams here. Welcome to the Poster Problem Clinic workshop. Poster Problem Clinic is a technique that is used to encourage learners to learn to work like a mathematician. It's built around the working mathematically process, which you have on the page in front of you, and in particular around the part that reads, read and understand the problem, plan a strategy to start the problem, carry out the plan and check the result, which derives from the book How to Solve It by Polya, which is 1945, but well and truly a classic. The first two sections of that don't require any pens. It's a time for reading and talking. Now we're going to learn to work like a mathematician, and mathematicians tell us that their work begins with an interesting problem. So I'm going to be showing you a problem just long enough for you to read it. It will go away, then we'll reflect on what you read. No pen or pencil is required until we agree that we're ready to start the problem. If you feel tempted to pick up a pen or pencil before that, well, maybe you'd best sit on your hands. Okay, here comes the problem. Okay, the problem's gone away, but it will come back in a moment. It's gone away so you can reflect on what you read. It's a literacy learning process called read and retell. So retell to your partner what the keywords are and what you think the important information is in the problem. And I invite the leader, when that's been chatted about for a moment or two, to make a public summary, or perhaps on the board, of what people think this problem's about. And then the problem will come back again, and then we'll move on from there. So pause the video just for 2 or 3 minutes while that gets organised. Mathematicians had to think about that problem now and recognise that the key things in it involve 5 twos, that there is an equation involved because we could see the equal sign, and that equation has to have an answer of 1, and that we have to combine, that was the other key word, combine the 5 twos to get that answer equal to 1. But they're not ready to start yet. That's the understanding of the problem. Where do they start? That's the next question. And they would probably dig into their strategy toolbox and open it up and see what there is that they could use that has been successful before. The strategy toolbox is on your screen,
and the strategy toolbox is on the Working Mathematically page that guides you in learning to work like a mathematician. Pause the video now and have a look at the strategy toolbox and see if there's something that you can use to start off this problem. Might not be the end of the problem, but just to start it off. Don't start the problem, just look for where to start.
Now I'm sure you're ready to start. You can even put your pen in your hand, but just hold it for a minute there. The kids are ready to go in the classroom, but let's us pause as teachers for a moment. There's an opportunity here where we might add a little bit more guidance just before we say go. Here's an example of what I mean. The video will tell you when you can start.
Now you've talked about where to start. One of the ways you might have thought of was breaking the problem into smaller parts. To make something out of 5 2's, you need to make some parts before you get to the 5 2's. So you might look at using 0 2's or 1 2 or 2 2's or 3 2's or 4 2's or 5 2's. You know you can't go any further than that because you're only allowed to use 5 2's. And then you could look back and say, well, 0 2's, I don't even get started. That doesn't work. 1 2. 1 2 is 2, but I can't do much with it. Can't do anything with it, really. It's just 2. But if I have 2 2's, then 2 plus 2 is something that I can work out. And 2 take away 2 is something I can work out. And 2 times 2 is something I can work out. And 2 divided by 2 is something I can work out. And that gives me some new numbers to play with.
Terrific! Everyone has one solution. Perhaps more than one solution has appeared. Where you go from here in the clinic depends on the class and your objective. If the objective is to get one solution, then the effort so far isn't really worth it, and it wouldn't be a problem. It would be an exercise. A good task is the tip of an iceberg, and that iceberg is worth exploring. You might make a whole lesson of this Professor Morris puzzle, and we will in a moment, but first consider an alternative use of time. My first experience of poster problems was teaching at Elwood High School in our mathematics laboratory, and my colleague Roland Seidel would put a new problem up on the display board in the corridor outside the maths laboratory where there was a high traffic flow. People did develop interest, and at times kids were making suggestions, either just dropping in or bringing things that they'd worked out on paper, and Roland would put them up around what was displayed. Later in my career, in my Year 2 and Year 5 classes, I used the same idea, but I would introduce it on a Monday for 10 to 15 minutes and get as far as we are at the moment, having just started. And then I'd leave the problem open for the rest of the week and on display as a poster, and invite the kids to work at it any time they had spare time or at home with their family. And that got some interesting results as well. And then on Friday, I'd have a plenary session based around what had happened during the week and what needed to still be explored with that problem. The great thing was I knew which kids I could call on to help me do that plenary session. Now let's explore the iceberg of this Professor Morris problem of 5 twos to make the answer 1 and see if we can find more than one solution. In fact, let's see how many solutions we can find. As each one is found, I suggest partners write the solution on the whiteboard and claim it with their initials. As you explore, remember that mathematicians tell us when they're working on a problem, if one way doesn't work, they just start again another way.
The problem didn't say I had to restrict myself to add, subtract, multiply and divide. It just said combine. I could combine 2 2s and make them into 22. That could be useful. I'm only using 2 2s and really there's an equation built in there already. It's got 2 times 10 plus 2 times 1. And I could also try 2 halves. That's another thing I can use, and 2 halves of course is equal to 1. So now I've started to get somewhere. I hope you've been getting somewhere with finding a way to combine 5 twos to equal 1. Perhaps you've already found a solution. Perhaps you've found more than one solution. Mathematicians love it when there's more than one solution to a problem. And in doing so, you've been dipping into your skill toolbox. The things you know how to do in maths to do some calculations. And there's a new skill that, well, a skill that will be new to some people, but maybe some of you already know. Let's have a look at it for a minute because it might help you find even more solutions. We already know, for example, that we can write 2 plus 2 plus 2 plus 2 plus 2 a different way as 5 times I've written 2, and that answer would be 10. As long as all mathematicians agree that that is a shortcut for writing the 2 5 times, 5 times I've written 2, 5 times 2, then everyone can use that shorthand. And that means we could also write 2 plus 2 plus 2 plus 2 as, yes, 4 times 2, which would give 8. And 2 plus 2 plus 2 as 3 times 2, which would give 6. 2 ways to write 6. 2 plus 2, super. That's the same as 2 times 2. And that's using our 2 times to get the answer 4. And if we only write 2 once, then it's 1 time that we've written 2 and the answer is 2. So this was a shorthand that mathematicians invented so they didn't have to write out long strings like that. And then sometime in history, a mathematician said, well, what happens if we have strings of times? So 2 times 2 times 2 times 2 times 2. How on earth could we shortcut that? And they agreed that what we could do is say, well, the number we're using all the time is 2, and we could show that it's used in a multiplication 5 times by writing it like that. And it shows that, and it's said to be 2 to the power of 5, and it means that 2 has been used in the multiplication 5 times, and the value of that is 2 2s are 4, times 2 again is 8, times 2 again is 16, times 2 again is 32. So that means you could write 2 times 2 times 2 times 2, and you would write it as 2 to the power of 4. And that would work out to be, I'll let you figure that out, and 2 times 2 times 2, that would be 2 to the power of 3, and 2 times 2, that would be 2 to the power of 2, and look, I'm using 2 times there. That could be 2 of my 2's out of the 5 2's problem. And then there's just 2. Well, I'm only using that once. So that would have the value of 2. Oh, we'll go back and fill these in. Come with me. 16, yes, 8 and 4. And then a mathematician said, hey, wait a minute, we've got a pattern going here. 2 to the power of 5, 2 to the power of 4, 2 to the power of 3, 2 to the power of 2, 2 to the power of 1. What happens if we get 2 to the power of 0? Well, it must be whatever this pattern is. And this pattern is a halving pattern. Half of 32, 16. Half of 16, 8. Half of 8, 4. Half of 4, 2. Half of 2, 1. Hey, cool! We just discovered we could do this shorthand and lead to this interesting way of saying that 2 to the power of 0 has the value 1. Now wait a minute. In this 5 2's problem, we need 2's and we need the answer 1. Perhaps there's something here that could help us. If we could use... Oh, I won't. Oh, sorry, I've run out of time. I'll have to leave you to ponder that one and see what you get. Alright, you've had a good time working on that 5 2's problem, and that's terrific. And a mathematician is never finished with a problem. Someone always comes along and asks the next question, and then the problem can move on. So just to round off what we've been doing, learning to work like a mathematician, and we were using a Professor Morris problem to stimulate us to do that, let's just look at what's been happening. We've collected quite a lot of data, some of which were equations that equaled 1, and some of which were equations that equal other numbers. And we could do that in both cases using 5 2's. So we've found at least one and perhaps more solutions, ways of doing it to equal 1. Here's a challenge for you that you might like to try by yourself, with a group, or as the whole class perhaps building up a chart of results. Suppose I asked you, can you use 5 2's to make every value from 0 all the way through to 20. 5 2's to equal 0, 5 2's to equal 1, 5 2's to equal 2, 19, 20, and so on. It can even be a challenge to try with your family, and the family results can come back and be part of the class record. Okay, that's it from me for now. See ya!